Hey everyone. So let's talk about a very special class of computer systems. You probably never see them, but they are absolutely everywhere, running our power grids, inside pacemakers, and even in the airplanes flying thousands of feet above us. And they all share one unbreakable rule. They absolutely cannot fail. Let's dig into why. So, picture this. You're sitting in an airplane cockpit. Everything, and I mean everything, from navigation to the flight controls is run by computers. But these are not your average desktops. Nope. They have one single, non-negotiable job: to work perfectly on time every single time. So what do you call a system that can deliver that kind of insane reliability? Well, the answer is a distributed real-time embedded system, or DRE for short. And yeah, I know, it sounds like a real mouthful, but trust me, every single one of those words is critical. So let's break down exactly what they mean. All right, so to really wrap our heads around this, we've got to break that name down piece by piece. Distributed, real-time, and embedded. Each part tells us something super important about how these systems work. Let's start with the first one.
First up, distributed. So what's that all about? It just means the system isn't all crammed into a single box. Its parts, the sensors, the processors, the things that make stuff happen, they're all spread out, right where they need to be. A modern car is a perfect example. You've got sensors in the wheels, an engine controller under the hood, displays on the dash. They're all part of one big distributed system.
Okay, next up, real-time. Now this is the absolute heart of a DRE system. And it's not about being super fast, it's about being on time. A car's airbag has to deploy within milliseconds of a crash. Not a second later, not even a little bit later. Because in these systems, a late answer isn't just late, it's a completely wrong answer. And that can have catastrophic consequences. And embedded. What does that mean? Well, basically, this isn't your laptop. It's not running web browsers or spreadsheets. It's a special-purpose computer designed from the ground up to do one or two things perfectly, and usually with very tight limits on things like memory, processing power, and how much energy it can use. So let's put it all together now. A DRE system is a network of these specialized resource-limited computers spread out where they're needed that absolutely must produce the correct results within unmissable, super strict deadlines. It's this combination of things that makes them so unique and so incredibly challenging to build. So now we know what they are, but what really makes building one so different from, say, coding a website? Well, it turns out they play by a completely different set of rules that are way, way more demanding.
I mean, just look at the contrast here. A web app? It runs on best effort timing. If a page takes an extra second to load, sure, it's annoying, but it's not dangerous. In a DRE system, a missed deadline is a total failure. Web apps have the almost limitless resources of the cloud, but a DRE system is stuck with whatever limited hardware it has on board. Its goal isn't just performance, it's predictable, repeatable safety every time.
Okay, let's go back to that cockpit we were talking about to see how all of this stuff works in the real world. Modern avionics are one of the most safety-critical applications on the planet, which makes them the perfect case study. See, the old way of building planes was, well, kind of brute force. Every single function, navigation, communication, you name it, had its own dedicated computer box. They called this a federated architecture. And sure, it was safe because everything was physically separate, but it was also incredibly inefficient. It meant more weight, tons of complex wiring, and it was just crazy expensive to build and maintain. So, the solution is a much smarter approach called Integrated Modular Avionics, or IMA. The core idea is simple but revolutionary. Consolidate many different functions onto fewer, more powerful computers, and the benefits are just huge. It drastically cuts down on space, weight, and power use, which saves fuel. It also makes the whole system simpler, which slashes development costs and complexity.
But wait a second. This brings up a massive, and I mean massive, question. If you have a critical function, like flight control, running on the exact same computer as a non-critical one, like the in-flight movie system, how do you guarantee 100% that the movie app can't crash and take the whole plane down with it?
The answer is an absolutely brilliant software concept called partitioning. It basically creates these secure virtual boxes, or partitions, for each application. And these boxes enforce two unbreakable rules. First, you have space isolation. Each app gets its own private memory. Nothing else can touch it, period.
Second, you have time isolation. Each app is guaranteed its own specific slice of the processor's time. So a buggy movie app can't hog the CPU and starve the flight controls. It's like having totally separate computers, just done completely in software.
So we've focused a lot on airplanes, and for good reason. But what's really important to understand here is that this isn't just about avionics anymore. The unbreakable rules of these DRE systems are quietly shaping the future of technology all around us.
Just think about it for a second. The exact same challenges we've been talking about, strict deadlines, limited resources, and an absolute, non-negotiable need for safety, apply directly to the tech that's defining our future. We're talking autonomous cars, life-saving medical devices like insulin pumps, and the next generation of systems for space exploration. They are all built on these same core DRE principles.
You know, as our world gets more automated, our trust in technology is really our trust in these invisible, meticulously engineered systems. They are the silent bedrock that keeps us safe. The real question, as these systems get even more complex, is how do we keep proving, beyond any doubt, that they are truly unbreakable?
If you found this dive into DRE systems interesting, please share it with a friend or a colleague who you think would enjoy it too. And of course, make sure you're subscribed for more explainers that break down the complex tech that's shaping our world. Thanks so much for watching.